All right, we're getting into our last portion of the course here. The last portion of the course involves us looking at the kinetics of bodies using some different kinds of methods than what we've used up till now. So I should have put it up here, but the little block figure that I've used, we're moving into a different block now. Today we're going to look at the work energy method of dealing with the kinetics of particles and rigid bodies, and I'm going to kind of talk about both of them today to some level. The basic concept that we use whenever we're doing this method is the idea that you cannot create or destroy energy short of, nuclear reaction kind of stuff, and so we are going to keep our discussion short of that, and we're going to look at how to account for energy in motion of stuff, and that we can actually make interesting calculations using those accounting of energy type calculations and get useful output. So up here at the very top where I talk about conservation of energy, the basic idea here is that if you can sum for like one state versus another state of a system, if you can sum up the differences in the amount of stored energy, and energy can be stored in a few different ways. One of the ways that we can store energy is with what's called kinetic energy. What do you think kinetic energy is? Okay, it's not looking for anything super complicated. It's the energy associated with things moving. So when something is moving, it has energy associated with it, and we're going to look at that. We can look at what's sometimes known as strain energy, or sometimes this is also known as elastic energy. Okay, this is the type of energy that is going to be stored in a spring, right? So you can store up some energy, and the way that is physically stored is in the bonds of between the different particles that make up a material. Those little bonds can stretch and strain, and when they do that, it stores energy. So that's, we'll look at some springs here. We can look at things like gravity. Okay, that gravity is basically you can store energy based on a force field, which gravity is a force field, right? And where you are in the force field can change how much energy one particle would have relative to another. We have work, right? So this is another form that we look at. The definition of work, which is going to be the first thing that we touch on here, is, actually we'll just go right into that right now. The easiest way to think about it is if you have a constant force, you end up that force ends up doing work if, as it pushes, there is a movement that happens, and that there's at least a component of the movement that happens in the direction of the force. So to the degree that the force direction matches the motion direction, you have more energy transfer. Okay? And the way that we express that mathematically is that if you take I'll just call this work, and if you take F and cross it into that D vector right there, not cross, I meant to say dot, excuse me. If you take the dot product of those two, that ends up giving you the amount of work that was expended by that movement. Now, geometrically, the easiest way in my mind to understand this is to understand that you're basically taking the component of the force that is in the direction of the movement. So the easiest way in my mind to understand that is to actually drop a line here that's perpendicular to the direction of the motion and set up one of the components of the vector that goes that way, right? And that's the only component of that vector that's going to be doing work. The other component of the vector would push down like this, and there's no movement that's happening in that direction, right? So there's not any work that's done by that component of the force. The only component of the force that's doing work is the one that is lined up with the direction of the motion. Okay? And taking a dot product like this does exactly that. Doing a dot product between two vectors gives you that exact thing. The way I tend to understand it more intuitively is thinking about there being this angle in between the force and the direction of motion. Okay, so let's say that's an angle of theta between those two things. We would say, from a geometric standpoint, we would say this would be the magnitude of F times the cosine of theta, where that theta is that angle between the direction of the force and the direction of the movement. And then you'd just take that, all of that, and multiply it by the actual distance. Okay? So that's for a constant force. What if we have a variable force? All right, so that's kind of my next thing I want to talk about. What about a variable force? Okay, and so the answer to that is actually, not too awfully complicated. Let's kind of simplify this down and say let's say that we've already dealt with this idea that there could be a difference between the direction of the force being applied and the direction of the movement. Now let's look at a case where the two are actually lined up. Okay, so we have a force here, but now this force is variable. Okay, so you take it as a function of t, or you take it as a function of position. Let's just maybe say t here. Okay, so this is a variable force, and now it moves through this distance. Okay, tell you what, I'm going to actually, the easier one to explain here is if this is a function of position. So let's say this is a function of x, and that we'll say this is delta x. So that means that we started out at 1x, and we're going to another x. Okay. Well, one of the things that you notice here is that the equation that we would have for work, since the force is in the same direction as the movement, we would just say in this case that the work is going to be equal to F times delta x. Okay, and I could even say this as, instead of calling this work, I could say this is a change in energy in the system, right? Because if you actually think about up here, you're putting work in, that's going to be a change in energy. Okay. Well, what happens if I have this variable force of x, right? I called that F of x, right? I can deal with that if I make my little deltas super, super small and instead call this, d energy is equal to F of x times dx. Why is that a powerful thing for me to do? Basically take the sizes of things. I'm basically shrinking this distance here to where it is, almost nothing. That delta x, I'm calling it a dx, meaning it's almost nothing. So the reason this is important is that presumably your force, if it's a continuous kind of a function, presumably your force is not going to change much if you allow almost no change in x. So if you do this, then at that particular x position that you're at, any place where you're at, you can treat this f as if it's a constant, because those values are very, very tight with each other. And so what we can do with this then is we can say a larger change in energy is equal to an integral from x1 to x2 of f of x dx. Okay, so this is a little bit more powerful version of work done by a force. If that force varies with respect to position, then you can just do a little integral like this, and it ends up giving you the amount of work that was done over that, whatever that difference is in position of two things. So that's another thing that's, a handy relationship for us to know about. All right, next one. So we dealt with constant force. What about a constant moment? Okay, a constant moment or torque. Well, for that, we think about, we'll kind of make up a fictitious problem here, but one that's instructive nonetheless. Let's make up this thing where, let's say the mass of this body is 0, right? It's a massless body, the little spool, and that massless body has a massless rope attached to it, and I'm pulling with a value of F, and I'm reacting against that with a moment of M. Okay, we can make a couple of relationships here based on all the variables that I have up there. The first one that I would say is that M is going to be equal to what, would you say? If this is, if it's not accelerating, right? And, even if it was accelerating, we got 0 mass. We kind of, in order for this to make any sense at all, we would have to have it be as if it's not a dynamically changing velocity, let's say, of it. Well, if it's static in that sense, then how does F relate to M? Okay, and that's not a trick question. Just F times R equals M. Okay, so this is just F times R. Okay, so that's one thing. What about the little variable d there? So I'm getting you to think about here, as you wind up this rope on that spool, there's going to be a change in the angle of the spool, and there will also be a change in the position of the rope. And that's what I'm kind of depicting right there. Is there a relationship between the amount of rope that has come off the spool and the other variables that I have written up there? And I would say, based on our definition of radians, radians, remember, is arc length over radius. Well, d actually kind of represents an arc length because it represents an amount of rope that's being unwound off of this circle, okay? And radius is r, and theta is measured in radians, okay? So this tells us here that d is going to be equal to r times theta, or theta times r, either way. Okay, so those are two relationships that come off of this little diagram. Okay, well, let's now combine that with what we just came up with a second ago. How much work is done by the force F? All right, how much work is done by the force F? Just F times d, right? Okay, well, let's actually do some substitutions here. So work is equal to F, not F, let's substitute in for F. Let's substitute in M over R. Okay, and what about D? Theta times R, right? Those R's are the same. And so what we see here is that if you have a constant moment that you're applying, then the amount of work that that moment does is just equal to m theta. Okay? And I won't spend time trying to really derive it here, but what do you think if you had a variable moment, and let's say that variable moment was m as a function of theta? Okay. What do you think you would have as far as the amount of work done in that case? based on what we did a second ago for our more linear case, right? Yeah, you would integrate from theta 1 to theta 2, for instance, if you had two different theta positions on this thing, where m is given as a function of theta, and you do that d theta. Okay. All right, so those are a couple of our foundational things here in terms of how do we evaluate how much work a particular torque, moment, or force have done throughout a particular range of motion. Okay, and we can do that if we have constant moment or torque, that's super easy. We can also do it if we have a variable moment where it's given in terms of the amount of displacement. All right, well now let's look at some really common cases. All right, here we have a little block of material. That little block of material is being pushed by a force of F. Okay, the little block of material, I don't have it written up here right now, so I'll write it on there. Has a mass of M. Okay, and as a result of this force pushing on it, it may have two different velocities, which I have listed up there as V1 and V2. So the first thing that I will say here is that based on our definition of work, okay, we would say here that work is going to be equal to F crossed with D, right? That's what we had a second ago. For our particular problem that we're dealing with here, we are talking about a force applied in the x direction, right? The x component of that force, because that's what's lined up with the direction of motion. And the d that we have there is delta x. Okay? Now, based on our familiarity with how energy works, it can't be created or destroyed, right? There's no place for energy to just vanish, right? And so if we have a situation where this block is sliding on a frictionless surface, I'll add a couple more in there too. It's in an environment where there's no air resistance. It has basically nothing else acting on it. It just has this force of F, of which F of x acts in the direction that it's moving. That energy's got to go somewhere, right? There's an energy associated with, so if F of x, or the x component of F and delta x, if both of those values are non-zero, there's been an energy added to the system. And so that energy has to show up somewhere. And the way that it will show up is that change in velocity. Okay? And so that's what we'll do here. It's based on conservation of energy. I'll write that as a heading here. Okay? Based on conservation of energy, the change in kinetic energy and over the years I've seen a few textbooks. I have not always seen them use consistent letters to talk about some of these different values, and so what I a lot of times will do is just write it out and say I'm talking about kinetic energy here. Okay, so the change in kinetic energy then is going to be equal to that amount of energy that is being applied. F of x delta x. Okay, that's if we have a constant force, right? Well, again, like I said before, one way to deal with it if it's not constant is you can take these differences down to where they're super, super tiny, right? I can take this difference in kinetic energy, and instead of taking a finite difference of kinetic energy, I can take an infinitesimal difference of kinetic energy by calling this d instead of delta. Okay, and this is going to be equal to, now I'm okay with this f of x being a function of x, and it's going to be over a tiny little change in position dx. Okay, so that's if I've got a a variable amount of force. Well, now I can integrate both sides of this. And what I get on the left side is a change in the amount of kinetic energy okay. On the right side, based on what I just said a second ago, as it moves from one position to another, under this force, this x component of force, it's based just on that integral. All right, so far so good, but we actually have more information we can apply based on stuff that we've studied earlier in this course. So one of the things that we know, for instance, is Newton's second law. Oops. Okay, Newton's second law says f of x, or the x component of f, I should say, is equal to m times the x component of acceleration. Okay, so based on that, I can do another substitution over here. I can say that my change in kinetic energy is just going to be equal to the integral from x1 to x2 of max, right? M times ax. M is constant, right? M's not changing as this happens, so m can be pulled out of this, in which case I just have my x component of acceleration dx. All right? Well, now that's really interesting because we have another relationship here too. Okay, there's another relationship from one of our kinematic equations. Okay, this kinematic equation we have is that 1/2 of the difference in the squares of your velocities is going to be equal to this integral from one x to another x of your acceleration as a function of x. Okay, so this relationship now can be applied, and we can say all of that stuff in the integral to the right over there, this change in kinetic energy is going to be equal to m times 1/2 v2 squared minus v1 squared. Or, as is more common to write it, instead of writing it like that, we usually write it like 1/2 m v2 squared minus v1 squared. Okay. What if it started at rest? Okay. What if on the left portion over there, this thing had no velocity? If it has no velocity at the left position, then that just means that we can make this v1 0. And that's another form of the equation that you a lot of times see, is that if you just have one velocity and you want to know how much energy is associated with this velocity of this mass, you will often see kinetic energy written as just 1/2 mv squared. But what we're seeing here is that this is how you manage it if you're going from one state of a body where it's at one velocity to another state of the body when it's at another velocity. And so it's important to realize you can't just subtract the velocities. You have to deal with the squares of the velocities. Okay. All right, so that's our first one that we've dealt with here, is linear velocity, and that there's energy associated with linear velocity, and now we have an equation that we can use to evaluate how much energy is associated with a linear velocity. Well, what about rotational? Okay, because there's something else probably that we can do for a rotational kinetic energy. All right. There are more than one approach for you to kind of figure these things out. So I'm showing you a couple of different sort of ways to do this. This one's a slightly different way of looking at it than the other one. But let's say that we go back to our representation of a rigid body in one of its most simplistic forms, where I basically have two particles of mass. And those two particles of mass might be at different radius positions relative to a point that the particles of mass are rotating around. Well, based on what we just did, we can evaluate how much energy is associated, how much kinetic energy in a linear sense is associated with each of these particles, M1 and M2. And it's not complicated. We just say that this kinetic energy is just the sum of 1/2 M1 V1 squared and 1/2 M2 V2 squared. Right? Is that based on what we know and how we can relate omega of this body to the linear velocities instantaneously of mass 1 and mass 2, we can just say that this kinetic energy is just the sum of the two kinetic energies of the two particles. All right? Well, what's also good here is that I can relate this V1 and V2, like V1 for instance, is going to be equal to omega times R1. Right? V2 is going to be equal to omega R2. So I can do a little substitution there. Let me also factor out the 1/2. Okay? So I'll have 1/2 times M1 times, okay, here I have omega R1 squared plus M2 omega R2 squared. Okay. All right, well now if I actually do those squaring of omega R1 and omega R2, it allows me to set this up as M1 R1 squared plus M2 R2 squared, all of this times omega squared. All right. Well, how's that interesting? Well, I did this for two different particles. What if I had a larger number of particles? If I had a larger number of particles, the only thing that would change is I would have to sum up all of those particles. Okay? However many of them I had, in this case n particles, where I is an index that allows me to count through all the particles. And I would have here my masses and my radius values squared. Okay? And all that would be multiplied by omega squared. And I don't know if you remember it, but we actually talked about a quantity a while back. It was called a moment of inertia. And if you remember, this is exactly the same thing that we came up with to talk about moment of inertia. Okay? If we want to talk about it in a more continuous way, as if we have like a body where each particle has essentially infinitesimally small mass, but there's an infinite number of those particles, right? Then that ends up giving us the continuous form where you have the integral and everything. But either way, what you're dealing with there is a moment of inertia. And it's a particular moment of inertia. It's a moment of inertia about the center of rotation. Okay, times omega squared. So 1/2 I omega squared gives you the energy associated with that whole body rotating around that point. All right. Another thing I'll add here is that you can have differences, like you can actually talk about a delta kinetic energy like we did before, right? And if you do that, keep in mind that you can't just take a difference between your omega values. You have to do it this way. Okay, you have to take each of your omega values, square them, and then take the difference of those, if that makes sense. Okay, so as you have a change in the amount of angular velocity of a body like this, you figure out the change in the kinetic energy using 1/2 times the moment of inertia around that center of axis, or center of rotation axis, and then multiply it by your two angular velocity values, the difference in the squares of those. All right, so far so good. So those are my kinetic energy terms that I can use when I'm talking about the motion of things. There's other items that are often of interest to us, and so I'm going to cover now the idea of sort of linear springs, extension springs and compression springs. Okay? And so for the very first picture that you see up there, there's an equation for the force carried in a linear spring. Okay? So this linear spring that we have right here uses an equation that is F is equal to Kx. Okay? Well, this works also if you do it kind of as a, let me do this. I'll show you a little graph. Since K is just a constant, your force versus X right here is just going to be a straight line like this. I'll say that you can pick any point along this line, and you can say there could be a little delta X, and there will be a little delta F, and that slope of delta F over delta X is going to be equal to K, right? So that means this is delta F is equal to K delta X. Well, just like we did before, you can take that down into a delta. Instead of a delta, you can take it to an infinitesimally small difference. Okay, and that allows you to do some interesting things like integrate. Okay, well, recall again our energy equation. I drew the little picture here. So from this right here, our energy equation says that the amount of energy change in this case is going to be equal to F times X. Or in this case, I'll tell you what, I'll go ahead and say this is delta X. Okay, so F times delta X here. Well, with that, we can say that the little differential change in the amount of energy that we have there is going to be equal to whatever your F value is at a particular X coordinate, dx. And with that, we can actually figure out a change in energy is going to be equal to an integral from x1 to x2 of f of x dx. But what is our f of x dx? Okay. Our f of x is actually this equation up here, right? That is f as a function of x. And so I can put that in here as kx dx. Okay, k is just a constant. It's what it's called, a spring constant. X, though, is not a constant. And so when I think about the energy stored in this spring, as we go from one position of the spring to another position of the spring, that change in energy held in the spring is just going to be equal to that integral right, which is just k times, okay, x squared, I'll say x2 squared over 2 minus x1 squared over 2 if I evaluate that integral for x. Okay, but you don't usually see it written that way. You usually see the change in the energy being equal to 1/2. You pull out that 1/2 that's in both of those terms, k times the difference in the squares of your two x positions. Okay? Now it's possible that one of your x positions is 0. Like you have 0 deflection in the spring, meaning that you've got 0 force in the spring as well. So if your starting position, x1, is that relaxed position for the spring, this is where we often see that energy stored in a spring is equal to 1/2 k. And what I'll actually say here is that there's a letter that's often used here, lowercase delta, like this, 1/2 k delta squared, right? That's if you have an absolute deflection of the spring, an absolute change from 0 deflection, where you have 0 force, to some other deflection value. That's the delta that you're talking about right there. So that would actually be like, let's say, between here and here, right? This would be the delta for the second case there, right, for F2, right? So anyway, both of these are useful. All right, so that's for linear springs. What about for torsion springs? And I know this can end up feeling a little bit boring going through all these, but I want to give you an idea of where these equations come from for the different kinds of energy that we are going to evaluate. Okay, a torsion spring is one kind of like this picture that I have drawn right here. It's, a good example of this that everyone's familiar with is the spring that actually tends to close clothespins, right? You see a little wound up spring, and it's, basically tries to take the two things and create this rotational force around the pivot point for a clothespin, and it tends to close it. Well, torsion springs can look different than that, but it always tends to have this tendency to try to rotate something. Okay? And so with this idea of our torsion spring, maybe starting out at some relaxed position, and then you twist this body by an angle of theta, which begins to start putting a torque in our torsion spring. That equation that we use there is that m as a function of theta is going to be equal to just k theta. And that's assuming quasi-static, right? You're not taking any of that applied moment m and turning the energy from that into a kinetic energy just yet. We're dealing with just this case of that moment twisting up the spring. So it's just m of theta is just k times theta. Okay, well, I think we covered this a minute ago. What is our equation for torsional energy? Okay. Torsional energy, and actually maybe I can state it this way, where a change in torsional energy is going to be equal to your moment as a function of theta. Okay. I'll just take, right now we're going to deal with it if it's constant, but m times delta theta. The next step here, I'm going to say, well, what if you take that little difference and you make it go to where it's extremely small? Okay. Well, then that's just going to give you m, which is, you can take that as a function of theta. Since we have such a tiny change in torsional energy and such a tiny change in theta, then over that tiny little change, it's fair enough to say that m of theta remains constant over that little bit, and that allows us then to integrate this and come up with a change in torsional energy. And it's just going to be equal to the integral from one theta to another. Okay, so that's kind of like a starting theta and an ending theta of m of theta d theta. For our particular case, this is going to be equal to k times theta d theta. All right. And so if we actually do this, this ends up giving us k times theta 2 squared over 2 minus theta 1 squared over 2. Or the way that that's written more commonly is that we have 1/2 k times theta 2 squared minus theta 1 squared. All right, and I mean, again, I'll mention that this is for a change in torsional energy. Which, by the way, all springs that we're talking about, the actual category that we're in is something like strain or elastic energy. That's the physical mechanism that's storing the energy, is the idea that you're stretching bonds, right? You're actually inside the material. Atomic bonds, or just the bonds between the different little particles that compose the material, are stretched, right? So that ends up being a way of storing energy. If you're talking about absolute, energy in a torsional spring, generally we just say 1/2 k times, maybe I'll say theta squared, where theta is the absolute angle through which the spring has been moved. In other words, the angle relative to the spring being relaxed. All right. That covers pretty much all of what I wanted to touch on, but I'm actually remembering here that there was one thing I wanted to specifically call out when I first went up here and was talking about constant forces. So I'm going to go back up here for just a moment. Okay. When you're dealing with a constant force, one of the most classic examples of this is when you are in a gravitational field, right? So you imagine a massive body, okay? And let's say this massive body might be at two different heights. So in other words, at one point in time, the body might be in one location. Another point in time, the body might be in a different location. And that you end up with a difference in the amount of height, right? So delta H. Okay. Well, how much force is pulling on it? Well, it's going to be the weight, right? And so, this weight is, you can express that as like the mass of the body times the acceleration of gravity in both cases. What's the energy difference, okay, from state 1 to state 2? Okay, so this is specifically for gravity. Okay, your delta energy is just going to be equal to the amount of force pulling on this multiplied by how far it moved, because that's how much work would have to be done in order to lift it. So that would be just m G delta H. Okay? And I meant to call that out right at the very beginning. It slipped my mind to mention that. All right, so that covers the elements that we need to be able to solve a whole lot of very interesting problems. All right, so that's what we're going to do right now, is do an example problem.